Hi everyone, welcome to the section on Introduction to Neural Networks and Deep Learning. So this is our first section on neural networks and deep learning. So this is introductory section on neural networks and deep learning. In the sections to follow, we will study neural networks and deep learning in detail. We will study everything related to neural networks and deep learning in the coming sections, where we will also implement those with PyTorch. That is, we will solve the projects on neural networks and deep learning in PyTorch in the coming sections. So this is the introductory section of our neural networks and deep learning. Let's see what we are going to cover in this introductory section. So basically, first we will learn about the perceptron. So perceptron is an artificial neuron which is made by the scientist inspiring from a real neuron. So real neurons are present in our brain. So based on that idea, the artificial neuron, which is now called as perceptron, are developed by the scientist. So we will discuss in detail what is the perceptron and how we can use perceptron to build a neural network. Then we will discuss how we process features with the neural network, what are the weights associated with the features, and what are the activation functions of a neural network. Then in the third topic, we will learn how neural networks learning. So we will see neural network learn in two stages, that is the forward propagation and the backward propagation. Then in the final topic of this section, we will see the rise of a deep learning. We will discuss why deep learning is an important component of an artificial intelligence, why deep learning is helping us, what are the important applications of a deep learning. So I hope you will enjoy this section. Thanks for listening, and I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the fundamental concept of perceptron. That is, what is the definition of perceptron, what we can do with the perceptron. So perceptron is the fundamental unit of any neural network. With the help of perceptron, we can do a lot of things, like we can perform any kind of mathematics with the help of perceptron, like addition, subtraction, taking logarithm, exponent, or any kind of simple and any kind of complex mathematics. Similarly, we can do regression analysis with the help of perceptron. Similarly, we can perform classification with the help of perceptron. So there are many things which we can do with the perceptron. So what is the definition, or what is the concept of the perceptron, or from where the concept of the perceptron arises? So we know that in our brain, there are millions of neurons present, and they are interconnected with each other with the help of electric signals or electric pulses. Look at this neuron. Now this neuron is connected with this neuron, and this neuron with the help of electric signals or pulses. This neuron is getting inputs or the information from the previous neurons, and after processing the information, it is passing the signal to the next neuron. So in this way, every neuron has some input signal and some output signal. So here is another visualization of the brain neuron. Here we have written the input as a dendrites. These are the label for the inputs which are going into the neuron, and this brain neuron will do some processing with those input, and then it will generate the output for the next neurons. So the output of the brain neuron is axon, and the input to the brain neurons are called the dendrites. So this is another way of understanding the concept of a brain neuron. So inspiring from the working of a real neuron or the brain neuron, scientists developed the artificial neuron in the lab. So that artificial neuron is called perceptron. Here, this is our perceptron, and it is getting two kinds of input. Here we can see that X1 is the first input to this perceptron, and X2 is the second input to this perceptron. So what this perceptron will do? So this perceptron will do some processing on these inputs, then it will generate output for the next neurons. Okay, so this is our real neuron, and this is our artificial neuron. So this is present in our brain, so that's why it's a real neuron, and this is a neuron which is created in the lab by the scientists. Therefore, it is known as artificial neuron or the perceptron. So we can see that here the inspiration of the perceptron is from the working of a real neuron which is present in our brain. Now, here again, we can see the perceptron. Here the perceptron is getting two inputs, x1 and x2. Here we have associated the weights with both the input. So the weight associated with x1 is w1 and the weight associated with x2 is w2. So what is happening here? Here our perceptron, this is our perceptron. It is getting input and it is performing addition on the input. If we see the output equation of this perceptron, this is the addition equation because the first input to this perceptron is w1 x1. This weight will be multiplied with this feature x1 and this weight will be multiplied with this second feature x2. And when they reach to the perceptron, they will be in the form of w1 x1 and w2 x2. So what perceptron is doing with both these input feature, it is performing the addition. So addition is one of the simplest form of mathematics. So we can add two input signals easily with the help of the perceptron. Now, student, this is the simplest form of a neural network. In a neural network, we have three kind of layers, basically. The input layer, the hidden layer, and the output layer. So the input layer is responsible to providing the input to the neural network. So mostly the perceptrons on which we are working or we do processing are present at the hidden layer. So this is our one perceptron. So this is called the simplest neural network because it has only one hidden layer and only one perceptron in the hidden layer. Now this perceptron will do processing on both these input signals or inputs, and then it is giving output to the output layer. So this is input layer which is responsible to providing input to the perceptron. This is the perceptron which is present at the hidden layer of a neural network, and this perceptron is responsible to do some processing with the input signal, and after processing, this perceptron will give output to the output layer of the neural network. So neural network has three kind of layers: input, hidden layer, and the output layer. Here we can see that the output is again the sum of the two input signal because here the perceptron is again performing the addition. So the important perceptrons are present at the hidden layer. That are the perceptron which do processing on the data. The neurons present at the input are only responsible for supplying data to the neurons or the perceptron which are present at the hidden layer. Most of the processing of the data is performed at the hidden layer, and after processing, the hidden layers providing output to the output neurons. So this is the simplest neuron due to two reasons. The first reason is that we have only one hidden layer, and the second reason is that we have only one perceptron in the hidden layer. Now, this is another form of a neural network. Now, we can see that here we have more than one neuron in the hidden layer. Again, we can see that the hidden layer is one. Here, there are no more than one hidden layer. This is our hidden layer, but this time we have two neurons in the hidden layer. Since they are hidden layers, we can call it H1 and H2. That is, they are the perceptron or the neurons of the hidden layers. Okay, now this neuron is getting signal from both of the input. That is, it is getting signal from X1 and X2. Similarly, this neuron is also getting input from both of the inputs, that is X1 and X2. The weights associated with those inputs are different. That is, X1 is going to H1 with the weight W11 and it is giving signal to H2 with the weight W21. Similarly, the weight of X2 with H1 is 12 and the weight of X2 with H2 is W22. So the weights are different. However, every input is connected with the neuron present at the hidden layer, and similarly every hidden layer neuron is connected to the neuron present at the output layer. Since every neuron is connected to the previous neuron and the neurons in the next layer, therefore the neural network is also known as fully connected network or a fully connected neural network. So this is the great example of a fully connected neural network where we have two perceptron in the hidden layer. Now we can observe one more thing. We just have added one more perceptron in the hidden layer. If we see the previous neural network, it had only one perceptron. Now we just have added one more perceptron, and we can see that a neural network has become more complex. So the complexity of a neural network increases exponentially if we increase the number of perceptron in the hidden layer. So hidden layer is still one. There is only one hidden layer still in this neural network. We just increase one more perceptron. This is the bias associated with this perceptron, and this is the bias associated with this perceptron. Similarly, this B3 is the bias associated with this output neuron. So the most important neurons, which are perceptron, are present at the hidden layer. They are responsible to process the data which they receives from the neurons present in the input layer, and after that they provide the output to the neurons present at the output layer. This is another example of a multi-layer neural network with two layers of a hidden neurons. Now we can see that here we have two hidden layers. This is our first hidden layer. This is our second hidden layer. This is our input layer, and this is our output layer. Here we have 5 neurons in our input layer. This is our first hidden layer with 1, 2, 3, 4, 5, 6 with 7 perceptron, and here we have 3 perceptron in our second hidden layer. Similarly, in our output layer, we also have 3 neuron. Now, if we see that every neuron is connected with the previous neuron and the neuron in the next layer, that's why the neural network is also known as a fully connected layer. So this is a multi-layer neural network. Now, student, if we see that we have 2 hidden layers. So if in a neural network, we have 2 or more hidden layers, so that neural network is called a deep neural network. So the concept of a deep comes from the word depth. If the depth of neural network is 2 or more than 2, it becomes a deep neural network. So this is our deep neural network because here we have 2 hidden layers in addition to input layer and the output layer. So we have 2 hidden layers present. That's why the depth of this neural network is 2, and it is considered as the simplest form of a deep neural network. It's not the simplest form of a neural network, but the simplest form of a deep neural network with depth equals to 2. Now, come back to the basic perceptron. In addition to perform simple addition, what we can do with the perceptron? So basically, with the help of perceptron, we can calculate the average of the input. If you see, this is 9, this is 3, and this is -6. If I add all of these values, I will get 6. So here, this addition sign will perform the addition, and after adding, we are dividing by 3 in order to calculate the average of the input signal. So therefore, the average here is 2. So we can see that after addition, we can also perform the averaging with the help of a simple perceptron. So we know that we can do any kind of mathematics with the perceptron. We can also do regression and classification with the perceptron, which we will study in detail in the coming lectures or in the coming sections of the course. This is another averaging machine. So we can see that here we have assigned the equal weight to all the input, that is 1/3. So what will happen? This 1/3 will be multiplied with 9. So we will get 1/3 into 9. This 1/3 will multiply with 3. We will get 1/3 by 3. This 1/3 will be multiplied with this -6. So we will get 1/3 -6. So if we solve all of this, we will again get a value equals to 2. So this is another way of performing averaging. Now here it is a weighted average machine. Weighted means that we have assigned the different weight to the input features according to their importance. Now this is 9, this is 3, and this is again -6. We have 3 inputs called x1, x2, and x3. We can also call them as a feature of our data. So every feature has different associated weight. So if we want to write the equation first and then put the value, we can do that. Like this branch has a weight W1, so it will multiply with X1. So this branch will give a signal called W1 X1 to this perceptron. Similarly, we get W2 X2 from this perceptron, and from third input branch we get W3 X3, and it will reach to this central perceptron. Now this perceptron is performing addition here. So the equation is W1 X1, which is coming from this branch, W2 X2, which is coming from this branch, and W3 X3, which is coming from this branch, and here is the addition. So this is the output of this neuron. So if we put these values here, we have X1 9 and W1 4. So this is our first product, this is our second, this is third, and here we get the addition from the perceptron and we get 33. So we can see that we can do a lot of things with the help of a single perceptron. So in general, how many inputs we can provide to the single perceptron? So we can provide any number of inputs. Here we can see that we have inputs from X1 to Xn. So the weight associated with X1 is W1. Similarly, with X2, we have the weight W2. And with Xn, we have the weight Wn. This is our bias, which is going into this perceptron, which is performing addition for us. So this is the total equation. Here we have n number of input features. So the equation is the sum of all the features. Here I is from 1 to n. And it is Wi xi plus b. There is only one bias, but we have n number of input feature to this perceptron. So we can write the output equation of this perceptron like this. So if I put I equals to 1, I will get W1 X1. If I put I equals to 2, I will get W2 X2. If I put I is equals to 3, I will get W3 X3. Similarly, if I put the last value of I, which is n, I will get Wn and Xn. So basically this Y is basically W1 X1 plus W2 X2 plus W3 X3 plus B. And this is the compact form of the equation. So this is the general representation of the basic perceptron. So we can see that we can give as many input to the perceptron as we can, but there is only one bias associated with each perceptron. So in this lecture, we learn about the fundamental concept of a perceptron. We see we can perform a simple addition with the help of perceptron, and we also learn from where the concept of perceptron arises. In the coming lectures, we will make more use of the perceptron. We will see how perceptron can be used in regression and classification. So I hope you understood this fundamental lecture on the perceptron. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn how we can process features with the help of perceptron, how we can associate weights with the features, and what are activation functions, why they are important to improve the performance of the neural network. Okay, let's start with the example. Suppose few candidates appear for interview in a company, and company's output after the interview will be either selected or not selected. That is, if the candidate is selected, it will be assigned a value 1, and if it is not selected, it will be assigned a value 0. Okay, the company will classify the candidates based on some qualities of the candidates. So these are the 4 qualities of the candidates, which are known as the features of the candidates. Based on these qualities, company will decide whether they will select the candidate or not select the candidate. So these features or qualities are the qualification relevant to the job, experience, communication skill, and address of the candidate. Now, we call these qualities as a features. Let's call them as X1, X2, X3, and X4. Now, these 4 features are the qualities of a candidate which is appearing in an interview. Let's see how we can process these features with the help of perceptron and make decision about the candidate. Okay, now X1, X2, X3, X4, they are the features of the candidates or the qualities of the candidates, and we are processing these features through a perceptron. Here we are getting the output from the perceptron or this simple neural network. Here perceptron is performing addition on these features. Therefore, our output is X1 plus X2 plus X3 plus X4. Now let's assign weights to each feature based on the job requirements. So we have four features. Now it's time to assign the weights based upon the importance of the feature. So we see that the qualification relevant to the job is most important feature. Therefore, the weight assigned to this feature is of highest value, that is 1. Similarly, experience and communication skills are also considered as important feature. So their weights are 0.6 and 0.3 respectively. Similarly, if we see that the address of the candidate, it might not be a very good feature in order to get the job. Therefore, the weight assigned to this feature is very small, that is only 0.01. Now let assign these weights to the feature and then process them with the perceptron. So here we have assigned the weight to each feature, that is W1 to X1. Similarly, we assign W2 to X2, W3 to X3, and W4 to X4. Now this will become our new output equation based upon the weights. So here we are getting W1 X1 from this branch. Similarly, W2 X2, W3 X3, and W4 X4. So that will be our neural network or perceptron score, which will help us to decide about the candidate. Now, if we assign all x1, x2, x3, x4 is equals to 1, then their values depend upon the weights associated with them. Now, this is 1 and this is also 1. So, x1 times w1, it will become 1 times 1. So, this is w1 x1, this is w2 x2, that is here, and this is w3 x3, and this is w4 x4. If we add all these value, we will get 1.91. So this is our perceptron score or a neural network score. Now, based on this score, we have to assign a value or a label, either 1 or 0, because 1 means the candidate is selected and 0 means the candidate is not selected. So how to transform this 1.91 into a decision? Now, for this, we need to model this output value of a perceptron or a simple neural network. Now, how to model this output? In order to model this output, we need an activation function. The reason is that this 1.91 is the output value of the perceptron for this particular candidate. If there is another candidate whose output will definitely be different from 1.91 based upon the weights associated with his qualities. Similarly, if we have many candidates, then the output will be different. That is, we might get a value of 0.81 at the output, 0.91 at the output, 1.1 at the output, maybe 2.7 at the output. So we will get the different values at the output. Then how to reach to the decision? So in that case, we need to model the output of this simple perceptron or a neural network. In order to model the output of a neural network and to make the decision, we need an activation function. So this is our activation function. Here we are using threshold-based activation function. This is the definition or the property of this threshold activation function. This threshold activation function will generate 1 if the output of neural network is greater than 1, and it will generate 0 if the output of a neural network is less than 1. So for this value, which is 1.91, this value is greater than 1. Therefore, the activation function will generate 1 and the candidate will be selected. So this is the first introduction of the activation function in neural network, and we see that activation function is used to model the output of a neural network. It ensures the consistent performance of a neural network. That is, the neural network score might be any, that is between 0 and to any highest value. In that case, in order to make a decision or in order to reach the decision, we need to model this output of a neural network. And for this purpose, we need an activation function. So activation function is important when we have to model the output of a neural network and when we have to ensure the consistency in the performance of a neural network. So this is the first introduction of activation function in neural network. We will discuss it more. There is a whole section on the activation function. So I hope you understood this lecture, that how we use activation function with neural network, how we process the features and weight with neural network or with simple perceptron. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will study how neural networks learn and what are the important stages or steps during the learning of a neural network. So neural network learn in two stages or propagations. The first is called forward propagation and the second is called backward propagation, or in short, backpropagation. So what happened in forward propagation? So basically in forward propagation, we calculate the error of the neural network. We know that error is the difference between the actual labels and the labels predicted by the neural network. So here we pass the data samples to the neural network and we get the predictions from the neural network, and then we will compare the predictions with the actual labels. So we will calculate the error during the forward propagation. If there is no error or the error is zero, then we do not need backward propagation, because if we see here the definition of backward propagation, that we propagate the error back to the layers of neural network and we update the weights and bias iteratively. So basically in forward direction or in forward propagation, we calculate the error of a neural network, and if there is an error, we propagate the error back to the neural network so that neural network can update the weights and bias. So in the coming iterations, it can perform well so that it can generate predictions close to the actual label. So these are the two propagations in which neural networks learn, that is the forward propagation and the backward propagation. So here is an example of a forward propagation. We have an input layer, we have an output layer, and we have a neural network, means this is our hidden layer. So here neural network is generating some predicted value. So this is our data set. We have 4 samples. So in the first sample, both the input are 0, that is the value of both features are 0, and the label assigned to the first sample is 0. The labels for the next 3 samples is 1. So what we will do, we will pass this data set step by step to the neural network and we will get the predictions. Then we will compare the predictions with the output or with the actual label of the data set. And if there is an error, we will calculate that error for the back propagation. So this is the example of forward propagation where we have the predicted value from the neural network. So this is our neural network. Since we have 2 features, so we have X1 and X2 here. We have 2 neurons in the input layer and the third neuron is a bias. Okay, this is our hidden layer neuron or H1, and this is our output neuron here, which is giving us the predictions. These are the weights associated with the features, and the value of bias here is -1. So what is happening during the first iteration? So during the first iteration, the predicted value of the neural network is -1. If we compare this -1 with this 0, definitely there is an error, and we need to propagate this error back to the neural network in order to update the value of these weights and this bias. So after calculating the error, we will transform this error into the loss function or the error function. So here we are simply squaring this error. This too is for mathematical convenience, that if we take the first derivative of this loss function equation, this two can be cancelled out with this two. So this is for the mathematical convenience. Now this is back propagation. What is happening in the back propagation? We have an error from the forward propagation. We are propagating this error back to the neural network. So that step is called backward propagation or back propagation. Here we are calculating the error by taking the difference between the predicted value of the neural network and the actual label of a data set. Now, here we are updating the weight. Here we are updating W1. Now, back propagation is used to update the value of weights and bias so that we can improve the performance of a neural network. Now, this equation is very important. If we see the left side of the equation, we have to improve the error. Improving the error means we have to reduce this error or we have to reduce this loss with the help of W1. So in the first stage, where we are updating this weight W1, we are reducing the error with respect to W1, or we are updating the W1 so that we can reduce the error. So it is the rate of change of error with respect to W1. Now, this term will be calculated with the help of these three derivative terms. So we can see that we have a very simple form of a neural network. Even then, we have three terms in the back propagation equation to update the weight W1. Now, how we can write this equation? So basically, in neural networks, we do not write error or we do not show error. But from the previous slide, we know that there is always an error present in a neural network, which is the difference between actual and predicted value. So how we have created this equation and how we have to write this equation. So basically here somewhere we have an error. Now this error terms contain y predicted value. So how we proceed from error to reach to the W1. So basically when we have to update the weight, we have to start from the error and we have to take all the parameters until we reach to that particular weight or particular parameter. So here somewhere we have an error. So from error, we will reach to output y, that is dE by dy, then from y to h1, then from h1 to w1. So first we will find rate of change of error with respect to our actual label. This actual label is important because we have to force the y predict of a neural network to reach up to this value so that the error becomes 0. So the first derivative is the derivative of error with respect to y. So here somewhere is error. So from error we will reach up to y, then from y to h1, and then from h1 to w1. If there are more hidden layers, suppose here if we have h2 as well, then from y we will reach to h2, from h2 to h1, and then from h1 to w1. So here we have a gentle introduction of backpropagation. We will discuss this backpropagation in detail in the coming slide. So here we can see the simple equation of a backpropagation where we are updating the value of weight in order to reduce the error. So it contains three derivative terms even in the simplest form. So this is the way of writing the equation. So similarly, if we have to write this equation for W2, we will write dE by dy, then the derivative of y with respect to h1, and then from h1 we will go to w2. So the steps are same whether we have to update this w1, this w2, or this bias value. So this term is called the gradient. Then we will multiply this gradient with the learning rate and we will add it to the old value of the weight. So the old value of the weight here is 1, and here we have to set the learning rate. Usually we set the small value of a learning rate. We have already learned about the learning rate in our gradient descent section or gradient descent lecture on regression analysis. So the value of learning rate is usually considered as a small value, that is 0.01, or even for neural networks we can use 0.001. So what we will do after getting this gradient equation, we will multiply this equation with the learning rate and then we will add it to the old value of the weight. Then we will get the updated weight. When we get the updated W1, similarly we will update it W2 and bias value. Then we will go for the second iteration and we will get again the predicted value, and then we will calculate the second error, and we expect the second error to be small as compared to the error which we obtained in the first iteration. So this is the way of learning a neural network. That is, in forward propagation we calculate the error, and in backward propagation we move the error back to the layers of neural network, and then we use this backpropagation equation in order to update the weights of the equation. So that backward propagation equation is the simplest form of the equation because here we are using the simplest form of a neural network. We will discuss more about the backpropagation and we will discuss more about how to write the equation of the backpropagation in the coming slides. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So till now we have some introduction about the neural networks. Now we know what is perceptron. We know from where the concept of perceptron arises. We know how to process the features with the help of perceptron. We also know something about the activation functions, and we also know how forward propagation and backward propagation works. So we can see that now we have some gentle introduction of a neural network in this section. Now it's time to get some introduction about the deep neural networks or about the deep learning. So basically this section is all about the introduction of a neural network and deep learning. Definitely in the coming section, we will learn in detail about the neural networks and all the networks which belongs to deep learning. Okay. So this is the paper which revolutionized the deep learning area. So that paper was published in 2012, ImageNet classification with deep convolutional neural network. Now, with the publishing of this article, we came to know about two important things. That is, for deep learning or for deep neural network or for deep convolutional neural network or for any deep learning network, we need large data set. So they provided us the large data set, which is called ImageNet dataset. And the other thing is that we need resources in order to run the neural network. That is, we need computational resources. We need high-speed computational resources so that we can process the large data set with the neural network. So these were the two important things which came to know, that we need large data set and we need high computational resources. So after the publication of this data set, many researchers have now created their own data set, which are considered as the large data set and which are useful for the deep learning. So this is our ImageNet dataset. So this ImageNet dataset has 1 million samples and 1,000 categories. So you can see that with 1,000 categories, we have 1 million samples. And in order to process these 1 million sample through a deep learning model, we need computational resources. So now these days, the computational resources are easily available. Definitely, we need GPU in order to process these images through a neural network, that is the graphical processing unit. And these days, the graphical processing unit are easily available in order to process the images through the deep learning model. Now, following are the most important deep learning models. They are considered as the state-of-the-art deep learning models, which has been designed by the scientists and researchers. So first are the VGG16, the ResNet 18, the ResNet 15. These are few state-of-the-art models which are convolutional neural network, and they are considered as the state of art in order to perform the image classification. Now, the second is long short-term memory or LSTM and its variant. So this deep learning model is used for machine translation or natural language processing or for time series prediction. So it is used to translate one form of language to another form of language. Like you can translate English into German or English into French. The next is autoencoder. So autoencoder is also a versatile deep learning model. It is used to compress the data and it can also perform image classification. Then we have generative adversarial network GAN. So these are the generative deep learning model which are used to generate the data from the given data. And they also have the ability to generate the data from the noise. The next state-of-the-art models are the transformers. So the two basic type of transformers are the vision transformer and the time series transformer. The vision transformers are used for image classification and the time series transformer are used for natural language processing or for time series classification and prediction. Now, what are the applications of a deep learning model and what we have achieved with the help of deep learning model? Now, with the help of deep learning model, the performance of face detection has been improved. Now, face detection is the problem where we have to detect the face in an image. Previously, in a classical methods, our accuracy was not as accurate as it is now with the help of deep learning model. So the first achievement is that now we have a face detector based on the deep learning model whose accuracies are close to 100%. The other application is the object detection. Object detection is considered as the most difficult task in computer vision and image processing. In object detection, we have more than one objects in a single image. We can see that this is our image and we have cat and we have monitor. Similarly, this is our second image and we have more than one different fruit in that image. So we have object detection, we have object detector, which are based on deep learning models, which can detect the objects very accurately and precisely. The another application is the financial forecasting. Usually the time series transformers can be used for financial forecasting, and LSTM are also being used for financial forecasting. So in financial forecasting, what we have a time series data about the stock prices. So based upon the past time series data of the stock prices, we do the forecasting about the next year or the next month. So this is called the financial forecasting, and it is being done now very accurately with the help of deep learning models. So the other application is a machine translation. This machine translation is being done with the help of transformer and with LSTM. So here is the example with LSTM. So we have encoder LSTMs and we have decoder LSTM. So in encoder, we have the LSTM, 5 LSTM, and in decoder, we have the 4 LSTM. So this encoder and decoder are based on LSTM and they are going to perform machine translation. That is, they are translating this English language into the German language. So in this lecture, we learn about the introduction of a deep learning model. We came to know that for a deep learning model or for a deep neural network, we need large data set and we need computational resources. So these are the two important things we need to know about the deep learning. Since the arrival of the deep learning, we have now quite a few number of data sets available which we can use for our deep learning model. We also have the computational resources available in the form of GPU, that is the graphical processing unit. Then we learn in this section about the few very important application of the deep learning, that is face detection, object detection, financial forecasting, and machine translation. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.